Okay, the MagLoop. So you've had a look at the sort of finished product. Still got some work to do on it. So what did I use? So I used an ESP32-C6 microcontroller. Mine was an Idea Spark, but the Arduino sees it as a SparkFun. Some Vero board, as it was called back in the day, or strip board. You could just use breadboard to develop it on initially. I did. Don't go soldering components on until you know they're right. 7805 regulator, because the motor requires 12 volts. And the ESP32 requires 5 volts. I managed to get the motor working on 5 volts before I had it driving anything, just to check it was working, but no. 7805 regulator, that provides 5 volts at 1 amp. It's a linear regulator, so it won't cause any interference. Has to be decoupled from the power supplies, so 0.1 microfarad front and back, one on the input, one on the output. 3300 microfarads on the output, that's on the 5 volt. 3300 microfarads on the input, the 12 volts. That's what 7805 looks like. Input on the left, common in the middle, output on the right. Been using those for donkey's years. Don't know how big a dime is, but I know how big a 7805 is. I used a NEMA 17 stepper motor. I made the mistake of using one with a normal drive rather than a reduced drive. For considerably more money, you can get one with a 6-to-1 reduction on. I did this using some gears. Oh, I haven't got those, hang on. Yes, I used the L298N stepper driver. I got a NEMA 17 stepper mount with fixings. Don't know where they went. NEMA 17 stepper motor, 42x40. And I made a gearbox. I used the 16 tooth and the 60 tooth. So it gives me about 4-to-1. And a belt, tooth belt, and an ESP32-C6. And then we come to the circuit. I'll do the circuit first. Today's episode of TechMaker is brought to you by an unbranded cup of chocolate. So you can build all this and get it set up just using the ESP32, and you can drive the motor from the 5 volt rail coming off the USB sockets that I didn't bother to draw in. But when you actually come to want to drive something, especially a 40-year-old variable capacitor, you're going to need a 12 volt power supply. If you've got a 12 volt power supply, you don't want to have a USB cord plugged in. So consider this to be a sort of finished product. It needs some tweaks yet. So don't go at getting circuit boards built for it or anything. The 12 volts comes in. First thing you see is the two capacitors. 0.1 microfarads to get rid of high frequency interference. 3300 to smooth any mains ripple. Standard practice when using any DC voltage regulator. Nothing unusual about it. 7805 regulator, that's the input, that's the output 5 volts. 5 volts feeds the L298N. 5 volts feeds the ESP32. Same again, 0.1 microfarads, and this time 330 microfarads, just to stabilise the 5 volts itself at low frequencies. So any interference that comes back through from the motor, because as you're driving a motor, there's little current surges that can cause the voltage to go up and down a bit. That's going to help. And any digital noise coming back off the ESP32, 0.1 microfarads will get rid of that. The stepper driver requires 12 volts from the input, requires 5 volts from the 7805, and a 0 volt return. We won't call it a ground because it's not grounded. There's 4 inputs from the outputs on the ESP32. I've used pins 4, 5, 6 and 7. They go into the 4 driver inputs. And then there's more than 4 wires on this, but it's a plug and it's a socket. What can I say? Doesn't matter. I think there's 6 connections on it, but you can't plug it in wrong. You just connect it up like for like and it'll work. So there you go. We're going to be using the Wi-Fi capability, which is why we need the ESP32C6 W-room. I'd love to know what W-room stands for. No idea, they're all call that. And that is your basic construction kit. I haven't added it all up to find out what it costs because I bought all the bits at different times. You may recall originally I had a smaller stepper motor. While it was pants, it wouldn't overcome the resistance on the variable capacitor. So there we go. Oh, 7805s are now up to 1.5 amps. They used to be 1 amps back in my day. That's the better view of the stepper. It doesn't. The pinouts are not in the order I've shown on the circuit diagram. There's the inputs there, which are labelled. It shows you what they are. Can't read them. Oh, ENA and ENB and in 1, 2, 3, 4. So these two will probably be positional feedback, so that it knows. Then you've got big driver IC, which is an L298N. On a heatsink, it does get hot. Then you've got 2 outputs there and 2 outputs there. Nothing too technical about it, don't worry about it. And that's dirt cheap. Then to control it, once again using Remote XY because I developed it ages ago. I've got many versions on here, but I'm only going to share with you the ones that work, which is this one. This is using the cloud controller. Again, we've got a position indicator that swings round like a meter. We've got a numeric value here, which according to how many steps your motor and gear setup can do and capacitor. Mine does about 515. We've got decrease by 1, increase by 1, decrease by 10. This is programmable in the code. Increase by 10. I've not decided if this is enough yet. It takes an awful long time to go from one end to the other. So I may make these 25 or even 50. But the fine adjustment you don't mind. You're going backwards and forwards to find the peaking point. So that's that. Source code as always. You can download the source code and combine it with the existing code that you've got. You can use this to connect to the app. But when you use the Remote XY, Arduino or iPhone app, it will connect to it. Code. Here is the Remote XY code. I've called it MagLoop 2025. I'll put that on GitHub. I'll put a link in the description. We'll go into it in a massive detail. This is just the connection between the software and the hardware. You don't really need to, there's nothing sensitive about this data. This is the structure for all the controls, the variables, button left and right 2. Those are the faster ones. Don't worry about the LED, I didn't use it. The circular bar, which is the one like a meter. The value, which is the text box. The connect flag, so we know when it's connected. There's the Pragma pack, which allows us to access everything. That's the end of the Remote XY code. This is my MagLoop code. This is the ESP32C6 version. I did build it on an Arduino originally, just because it's quicker to not one up. This uses the Stepper H library. Obviously you're going to want the ESP32 for your particular board and the COM port for your particular board. Mine's not showing because I've unplugged it. It's in another room. The pin A, pin B and switch are for a digital encoder. which I used in development. I'm not using it now. Just be careful your pin numbers don't conflict with these ones. These are the NEMA 17 motor pins. And yes, I've got the numbers in descending order because it was going the wrong way. But you can change them around, you can use different pins, whatever you need. The motor speed I've set at 60. Not sure about the steps per revolution. Tried it on a couple of settings. I need to experiment with it more. This is the stepper object that tells the motor what pins to look for. Instead of doing digital write in and out and the pin numbers, you just address the stepper motor and the stepper library will take care of it. So I always look at the current position of the motor, which always starts at 0, the required position, which always starts at 0, and then we're going to, as you press the buttons, the required position will go up, and then we'll increment the current position to go with it as we step the motor. Don't worry about this debouncing. If you want to know about debounce, you can find that on the net. It's not difficult. It's a little bit convoluted, but basically it always prioritises input A over input B. So it'll only ever register a change when input A changes. It'll register it whether it goes high or whether it goes low, and each time it'll look to see if input B is high or low. That will allow it to detect the direction and act accordingly. You'll see it shortly. Start off with state A is true and state B is false. That has to tie in with the way the logic is ordered in the if statements. Step size is 1 initially, no problem. Although I think you'll see further down I didn't use it. Counts per half revolution. So because the capacitor is doing a half revolution, not a full one, and because the motor is doing a lot of revolutions, we just set the limit of how many pulses we need to open it half a revolution. And you do it by just doing it gradually until you get there and make a note of the number. You can always add a couple of extra ones just in case. So, setup. We initialise the remote XY, use the serial ports for debugging, set the LED up, which I didn't pay any attention to, and then set the pins up with using input pull-ups so that you don't need external resistors if you're going to use the digital encoder. It's always handy to have a digital encoder as well. Then if you have connectivity problems, you can just go up to it and twiddle it, or you could run a 3-core cable to it. Set the speed first and tell the serial debugger we're ready. So the main loop addresses the remote XY handler, and each of the buttons, if it's pressed, we do something. Now, mine goes backwards. So if you click left, we decrement or reduce by 1 the required position. Obviously, if it's 0, it can't go backwards, as you'll see, because I've restricted it here. If you press the right button, we'll increment it by 1 or add 1 to it. And we then put a delay in, and we put a little delay in, and it's 150 milliseconds, because you can't guarantee a clean signal when you're talking to things over the cloud. So as it would be with a physical button, there could be some noise on the system. One press could be interpreted as multiple presses. So by delaying it after each press by 0.15 of a second, we reduce bouncing, we reduce erroneous signals. Doesn't cure them, but it does improve it a lot. So you can give it a firm stab and release, and I've not had any problems with it registering really, I'll be honest. Also, you've got to bear in mind with the touch screen, you don't actually have to touch it on an Android. You only have to go near it and it'll trigger it. Same thing again, but I've increased the step size. So I didn't use the step size variable because it was building the code. So the other two buttons at the bottom, the ones that say plus plus on them, we increment and decrement by 10, and again we debounce them. So because it could go negative, do crazy things. If it's less than 0, we make it 0. Don't let it go backwards. If it goes above the half counts, the half revolution counts, then make it equal to that, don't go beyond it. That's when you're using the encoder, you can swap that out instead of the one above. So if the current position is less than the required position, step the motor clockwise and it'll step it once. Each time it steps it once until it gets to it. Once it gets to it, it will no longer do it. If the current position is, that's if it's less than. If the current position is higher than the required position, then go negative, go anti-clockwise. And again, when the two values are equal, do nothing, just go straight through. Place them to the screen, print the connect flag, that just tells me it's connected. The circular bar can only go from 0 to 100. So we take the value we want to show, multiply it by 100, divide it by counts per half revolution. So that bar can only go from 0 to 100. I'll put a little delay in here. So if it's not connected, it was supposed to flash the LED, but in practice, I've used the wrong LED variable. That should be... You always find them at the last minute, don't you? It's LED pin. The problem is when you're developing, you look through your code so many times. Oh, so yeah, we've got digital right there and there, but not here. Lost it now, it's in the loop, isn't it? So that's what I really wanted, is if it's not connected to flash the LED, but you can tell on the app whether it's connected or not. So this is the debound circuit for the digital encoder, should you choose to use it. So it looks at state A, and it looks at this millis value. And this millisecond value and the debounce value take control. So as the state changes, it's always got to have a delay. It's always got to be 150 milliseconds since the last button was pressed. And it does the same sort of thing again. It sends it clockwise or anti-clockwise. It decrements or increments the value. And then we reset the states to the new A and B values. So that's a stateful debound circuit, and I found that to be very effective. I used it on the prototype, not used it here, but I've left the code in because I feel it's useful. So when we actually step the motor, we call these, and instead of sending a value in, we just send it one step. So we literally do one step of step size, which is 1 or 10. So we always step it once, regardless. It's legacy code from the other one. So do a quick flash of the motor, delay it by the motor speed, and then go back and get another one again. The initialized motor, which I originally used to wind it from one end to the other and back, because I'm using a belt drive, I didn't think it was very nice on the belt or the mountings of the motor. So I'm not using that anymore. I did remove one part of it, so it only went in one direction. I found the best way to reset it is to plug it in. Before you plug it in, just turn it so that the capacitor is fully engaged. Plug the power into it. That's it, it's set. What more do you want? Couldn't be simpler, could it? So that is it. That's the code. I'll put that on GitHub and I'll put a link to it in the description. So I hope you enjoyed the video. I welcome feedback on it. Then there's a couple of people on a MagLoop forum on Facebook who are looking to do remote controlled MagLoop controllers. I'm not claiming this to be a fully working product yet. There's still work to do, and I will post an update when I do it. But I thought after nearly 2 years, you might like to have an update. I'm not completely idle. We'll see how it goes anyway. Thanks for watching. Best 73s.